Okay, awesome. Thank you. Today we are going to cover section 3.5. Section 3.5 talks about rational functions. So we're gonna look at the definition of a rational function, the domain of a rational function, and the graph of a rational function. So that's the focus of today. We should be very familiar with what is a polynomial, right? Yeah, again, the class right before the spring break, I covered the definition of a polynomial. I started with the monomial, binomial, trinomial, and a polynomial in general. And what's the standard form of a polynomial? So assume we are familiar with the definition of polynomials. We know what is a polynomial. And also we only consider polynomial in one variable, univariate. We do not consider multivariate polynomials. So we only expect to see one variable, most of the time is x, in a polynomial. We know from the foundation class, if we add two polynomials together, we have a polynomial as the sum. If we subtract a polynomial from another polynomial, the difference is also a polynomial. If we multiply any two polynomials, the product is also a polynomial. But if we divide a polynomial by another polynomial, we not necessarily will have a polynomial as the quotient. The result not necessarily is a polynomial. Okay, the division of a polynomial is trickier. Sometimes when we divide a polynomial by another polynomial, when the remainder is 0, okay, we can say the result is a polynomial. But a lot of times the remainder is not 0. In those cases, when the remainder is not 0, the result is not a polynomial. Then what's the result? What's the result? The result is a rational function. We can see that as a rational function. What is a rational function? Rational function is a quotient of two polynomials. That's the definition for rational function. Rational function is the quotient of two polynomials. Numerator is a polynomial, denominator is also a polynomial. Obviously, x cannot assume values that will make the denominator be 0. Denominator cannot be 0 is a common sense in algebra. We all know that, right? And the definition, the name of a rational function is consistent with the name of a rational number, actually. If you allow me to spend a little bit of time to show you, rational number, any number that can be written in this form. What form? P over Q. P, Q are both integers. Q is non-zero. Any number that can be written as a quotient of two integers is a rational number. Rational number. And rational function, any function that can be written as the quotient of two polynomial functions. Of course, Q of x are not 0, right? It's not 0. Px, Qx are polynomials. Very similar, right? So hope this can help you to remember the name of this type of function. Rational function. Rational function is a quotient of two polynomials. For example, this function f of x, numerator 5x plus 17 is a polynomial with degree 1 is a linear. Denominator x squared minus x minus 6 is a polynomial. Degree is 2. So this is a rational function. A rational function look like that. And you can also look at those functions. They are all polynomial. They are all rational functions because they are quotients of two polynomial functions. Numerator is a polynomial, denominator is a polynomial, right? And those are rational functions. That's what a rational function looks like. Very important thing about rational function is the domain. Let's recall the domain for a polynomial function. Anybody remember the domain of a polynomial function? Think about a linear function is a polynomial. The corresponding graph is a straight line, slant straight line. Quadratic polynomial function, the graph is a vertical parabola, either opens up or opens down. Do you guys remember the domain for polynomial functions?
Is it all real?
Yes, thank you. Thank you. It's Kaida, right?
Yes, ma'am.
Appreciate your response. Exactly. You want to remember this. The domain of any polynomial functions is all real. It's all real. There's no restrictions for the values that variable x can assume in a polynomial function. All real. So you want to remember that. Domain for any polynomial functions is all real. But the story is different when it comes to rational function because there's a denominator. We all know denominator cannot be zero, right? Let's look at the 21 here. How do we find the domain for this rational function? How do we find the domain for this rational function? The important thing is we consider the denominator. X cannot assume a certain values that would make the denominator be zero. So for that purpose, we normally have to factor the denominator if the factorization is allowed, is possible. We have x squared minus x minus 6. We can factor this quadratic trinomial. This one is pretty straightforward, right? As -3, +2. -3 and +2 multiply to -6, add up to -1. So the denominator can be written as, can be factored as x minus 3 times x plus 2. We all know denominator can never be zero, cannot be zero. So that means x cannot be +3 and x cannot be -2 because if x assume +3, then this factor, let me show you what I'm trying to say. This factor, if you're plugging in x equals +3, since the +3 is the opposite of -3, they add up to 0, then this factor is 0. 0 times another factor, doesn't matter the value, the denominator is 0, and that is not well defined. So x cannot assume the value of 3. Same idea, x cannot equal to -2 either, because I bet, give me 1 second. Good to know we have accomplished so much, right? So many questions we have covered. Okay, finally. Apologize for that. X cannot be equal to -2 either because if x equals -2, we plug in here in this factor on the denominator. -2 and +2, they are opposites, so they add up to 0. Then this factor is 0. 0 times another factor is still 0. That would make the denominator be 0, and that is not defined. That is not well defined. So we need to exclude +3 and -2 from the real number set to find the domain of the rational function. So the domain of the rational function is all real except values +3 and 92. So let me know if that is clear. This is pretty straightforward and basic. And it's important though. It is important. Rational function in general does not have real as domain. The domain of a rational function normally have the format is real except a certain value or values. Those values will make the denominator be 0. So far so good, guys?
Yes, I understand it.
Okay, thank you. Next topic, we want to talk about the graph of rational function. Generally speaking, the graph of rational function, they are kind of like they have multiple branches. The simplest rational function is the reciprocal function, y equals 1 over x. And we want to spend a little time to look at the first two questions in Lumen for section 3.5 and get familiar with the graph of this rational function. Well, I hope you see the reciprocal function here is a rational function. The numerator is 1. Y is a polynomial. It is a monomial with degree 0. If you don't see it, go back the section right before the spring break. I explained a constant term is a monomial with degree 0. And the denominator, x, is a monomial with degree 1. So this is one of the most basic rational function. And we want to look at the graph of this rational function and its transformations. We should remember the graph for this rational function, the reciprocal function. It has 2 branches. The 2 branches are in quadrant 1 and quadrant 3. One branch look like that. The other branch look like this. All right, I'm going to stop share the note and then share the Lumen, okay? Stop share this one and then go to share website. Hold on a second. This one, the website. It's very small. Do you see Lumen, guys? Let me know.
Yes, we see it.
Appreciate that. Thank you.
Yeah.
Thank you for letting me know. Okay, the first 2 questions, right? Look at this function. Y equals 1 over x minus 4 plus 1. You might wonder, why does it have anything to do with rational function? Well, it is a rational function, by the way. If you write 1 as x minus 4 over x minus 4 and then add the 2 kind of like fractions expression together, you will see it is a rational function. But also you can see this is a transformation of the mother function 1 over x. I just shown you the mother function 1 over x, the graph, right? The graph of 1 over x has 2 branches in quadrant 1 and quadrant 3, like that, hyperbola. And this function is a transformation of the mother function 1 over x. We can see the transformation has 2 steps, right? 2 steps transformation. We minus 4 from x, and then we add 1 to the function. So if we see 0, 0 as the center of the reciprocal function, if we see 0, 0 as the center, kind of like a center of the hyperbola, right? Then how will the center change after the 2-step transformations here? Imagine you have the mother function of the reciprocal function. You have the graph of the reciprocal function. And you subtract 4 from x. How would that change the graph? And then you plus 1 to the whole function, to the y. Yeah, the first step, the transformation happens to x. The second step, transformation happens to y. So you subtract 4 from x. So you shift the graph horizontally, right? To the right or to the left, 4 units. Minus 4 from x. To the right or to the left. You subtract 4 from x.
To the left.
To the right. To the right. Because x have to be 4 units bigger than original in order to have the same y value. To the right, 4 units, okay? So the graph shifted to the right 4 units, and then this one is added on top of the function. So this one is easier. You plus 1, you shift upward. You minus 1, you shift downwards. Here's a plus 1, so upward. So this function is hard to, because we are using Zoom, it's hard for me to write anything on it. It's not allow me to write anything here. So do you agree? This dollar function is we can get this dollar function by move the mother function graph, the reciprocal function, to the right 4 units and up 1 unit. So the center of the hyperbola will change from 0 to 0, 0 to 4, 1. Which one has center 4, 1? 4, 1. I already have this chosen. This one has a center 4, 1. Yeah, this one has a center 4, 1. This one also has a center 4, 1. And this one has a center -4, 0. So this one is not. This one is out. And this one has a center 4, -1. But so this one is not right. So have to be the first two. But remember the mother function has 2 branches in quadrant 1 and quadrant 3, not a quadrant 2 and a quadrant 4. So the correct answer is B, is this one. I'm gonna try one thing to see, and you let me know if you can see it, okay? I'm gonna try. I heard that there's a whiteboard in Zoom. I'm trying to. I couldn't find it. I don't know if is it clear when I just verbal the process. Is understandable?
Yeah, I understand.
How about Ether?
Yeah.
Kind of. Yeah, the mother function is 1 over x. So the 2 branches, one branch on the top right, the other branch on the top left. That's the reason option A is wrong, because the location of the 2 branches is not right. Has to be this one, right? Or other 2. The reason the other 2 is not correct because their centers are not correct. Since these dollar function are achieved by moving the mother function to the right 4 units and up 1 unit, the center will be 4, 1.
If you want to show how it moves, you can put the original equation in the calculator that's right there, and then put the -4 in, so you can show the
calculator.
Yeah.
Oh, so let's try that. Function equals 1 over x. Huh? 1 over x. 1 over x.
You have to put the y in front of it.
Oh, okay. Thank you for letting me know. Yeah, so this is the graph, right? So can I shift it?
If you put the 4 in the equation.
Oh, actually, this with the graphing calculator this basically not a challenging problem at all, because you can just 1 over x minus 4 and then plus 1. Is shift to the right. If I can change a different color, let me change colors? Yeah, it shifted to the right 4 units and go up 1 unit. Okay, I'll let you to do this one on your own. Question number 2. Determine the rational equation for each graph shown beginning with x equals 1 over x. So the mother function is 1 over x, and applying your knowledge of transformations. So this question is also about the reciprocal function, which is rational, and its transformations. Let's see this one. Mainly, we want to look at the center, right? Yeah, so the center of this one is 2, 5. 2, 5. So that means we move the mother function to the right 2 units and then go up 5 units. 2. So I should enter equation. So it's a function y equals 1 over, since move to the right 2 units, so x minus 2, very important, minus 2. And then the numerator is 1. Yeah, that's, we move to the right 1 unit, 2 units, and then go up 5 units. So add a 5 to the whole function, and that is the result. I hope you see it. Basically, this problem is the opposite, the other way around the first question. The first question, we're given the transformation. We're trying to find the graph. This question, we're given the graph. We're trying to find the daughter function. All right. So the next question, next graph, the location of the 2 branches is right, top right and left bottom, right, bottom left. Let's see what's the center. The center is right here. Is -1, -3. -1, -3. So that means we have to move the mother function to the left 1 unit and down 3 units. Then we have y equals, yeah, on your scratch paper, you should write it down. You move the graph, since you move to the left 1 unit, so you're gonna add 1. You add 1 to x. Since you shift downwards 3 units, and you have a -3 to the function. All right, let me know if it's clear. The next one, similarly, we need to find the location of the center of the hyperbola. It is 4, -2. So it means we need to shift the mother function to the right 4 units and down 2 units. And then the corresponding function should be y equals 1 over x, that's the mother function. But since we we move the graph to the right 4 units, so we have to -4 from x and shift it downwards 2 units, so we -2, like that. All right?
Excuse me, Professor.
Yes.
So for me, okay, I'm trying to make myself understand this. So if I'm writing this equation, y is equals to 1 over 3 over x, that's a
mother function.
So the downward part will have to be by the x, right? Or by the side.
Horizontal change.
Yes.
Is you add or minus number from x.
Okay.
Since this one is shifted to the right, if you shift it to the right, you minus the number. Yeah, that one is kind of like anti-intuitive.
Okay.
We've mentioned this in previous chapters. Up and down is very intuitive, right? Go up is plus, go down is minus. But for x, if you shift the mother function to the right 4 units, you actually need to subtract 4 from the variable x.
Okay.
Yeah, because x needs to be 4 times 4 units bigger in order for the y, in order for the function to have the same y value.
Okay.
Yeah. And one more, let's finish this one. The center is right here. It is 94, 94.
94.
94, 94. Yeah. So let's start with the mother function y equals x 1 over x. It shifts to the left 4 units, go down 4 units. Since the horizontal change is to shift to the left 4 units, we actually need to add a 4 here. And vertical shift, since it shifted downwards 4 units, that is to minus 4. All right. You can really use the this one doesn't. You can, yeah, you could use the calculator to help you. You enter the function, you propose the function into the calculator to see if you have the function, the graph exactly the same with the given graph. Okay, I think the question, because we have a calculator, is become less challenging. Now let's go back the notes. We are going to look at the graph of rational function in general and talk about the asymptotes. Talk about asymptotes. No, that's not what I'm sharing right now. You are screen sharing. Am I still sharing the Lumen or I'm sharing the notes?
You're still sharing the Lumen.
Still Lumen?
Yeah.
Stop share and 3.5. No. Not this one. One more. This one. The notes, right?
Yes.
Question number 23 is very important. Through this problem, we want to learn how to find vertical asymptotes, horizontal asymptotes, or sometimes the rational function has slant asymptotes, and how do we find it? And holes, sometimes the hyperbola has holes, the rational function has holes for a rational function. Okay, let's get started. Asymptotes. The mother function, the y equals 1 over x has asymptotes, okay? Even this simple reciprocal function has asymptotes. The horizontal asymptotes is the x-axis, y equals 0. Because the two branches, this branch on the top right is extending indefinitely and get very, very close to x-axis, but never touch or cross it. Similarly, the other branch on the bottom left, also this is approaching to the horizontal scale. So the horizontal scale is the horizontal asymptote. It also have a vertical asymptote. Vertical asymptote is y-axis or x equals 0, because the branch on the top right is extending when x approaches to 0 from the right is extending to the y-axis. And the other branch, when x approaches to the 0 from the left, is also getting closer and closer to the y-axis, but never touch or cross. So this shows you asymptotes are very important to rational function. Even the most basic reciprocal function has two asymptotes. One is horizontal, the other is vertical. First question. How do we identify the vertical asymptote? I'm going to use V dot A dot. V dot A dot represents vertical asymptotes. So to find the vertical asymptotes for a rational function, ideally, we want to have both numerator and a denominator factored, especially when it's possible, especially when the numerator and the denominator might have the same common factor, binomial factor. The first question, we do not have to worry about it too much. If we want to factor it, we can do this. The numerator has GCF 2, so 2 times x minus 3. The denominator has GCF -2. We want the leading coefficient to be positive, right? If we factor -2 out, we have x minus 1. Be very careful with the sign. You can always distribute to double check your result. 92 times x, 92x, 92 times 91, positive 2. So as you can see, the numerator and the denominator, they do not have a common factor. If that is the case, that means the rational function has no hole. In the case, the numerator and the denominator has a binomial factor in common, that function has holes. I'll show you later when we encounter a question in that case. But this problem does not have a hole, all right? We have nothing to cross out. The vertical asymptote, in order to identify vertical asymptote is a vertical straight line. So it must look like the equation of the vertical asymptote must look like x equals a number. X equals one number. X equals the number that will make the denominator be 0. Okay? So basically, to find the vertical asymptotes, we factor the denominators. Yeah, suppose numerator denominator have no common factor. And we look at the denominator and we find the zeros of the denominator. This denominator only has 1 0, which is positive 1. In other words, is the value that will make the denominator be 0, because 1 minus 1 is 0, right? The function has a vertical asymptote at x equals 1. That's how we find the vertical asymptotes. It's okay if it's not very clear, because we have more to practice. Vertical asymptotes is x equals a value, and that value is a root of the bottom. What about horizontal asymptote? Horizontal asymptote, we look at the coefficient of the two polynomials. One in the top, the other is on the bottom. Okay? We can go back to the original form of the function before we factor it. Numerator is linear, degree 1, 4x minus 6. The leading coefficient is 4. Denominator is also linear, degree 1. The leading coefficient is 92. All right? And the horizontal asymptote is a horizontal straight line. So the equation of the horizontal asymptote is going to be y equals a number. Y equals 1 number. The number is the coefficient. If is the quotient of the two coefficients. 4 over 92. 4 over 92, which is -2. And that's how do we find vertical asymptote and horizontal asymptote. What happened to slant asymptote? Slant asymptote, only rational function whose numerator has a higher degree than the denominator has slant asymptote. In this problem, when the numerator and the denominator, the polynomials, they have the same degree, then the rational function does not have slant asymptote. It will only have vertical and horizontal. Let me say that again, repeat. How do we find the vertical asymptote and the horizontal asymptote? To identify vertical asymptote, we look at the denominator and find the value that will make the denominator be 0. And then let x equal that value. then we have the vertical asymptote. To find the horizontal asymptote, we look at the degree. Firstly, we need to make sure the degree are the same. Degree are the same means when you let x approaches past infinity or net infinity, when you let x approaches past infinity, let's say, the numerator and the denominator, they basically run to have the same speed, similar or equivalent speed. The difference is made by the leading coefficient. Since they are both linear, numerator is a linear function, denominator is a linear function. So when x approaches infinity, the numerator and the denominator basically have, similar speed to run to the infinity. Numerator run to the past infinity, denominator run to the net infinity because of leading coefficient, right? And the difference is made by the coefficient. How fast the numerator run? 4 times of x. What about the denominator? How fast the denominator would run? 92 times of x. So we put them together, 4 over 92, 92. That is the horizontal asymptotes. Does that make some sense? Horizontal asymptotes, if you consider horizontal asymptote is the horizontal line that the two branches will use, at least one branch, when the x approaches infinity or net infinity, the function approaches to the horizontal straight line. Or the limit when x approaches infinity. Does it make some sense?
Yep.
Okay. Yeah. All right. And you have the graphing calculator. You can enter this function in a graphing calculator and help you to understand it. All right. So we found a vertical asymptote and a horizontal asymptote for this example. Next one. This rational function, numerator has degree 1, denominator has degree 2. It's different, right? Okay. As I mentioned, ideally, we want to have both numerator and denominator factored. Numerator cannot be factored. It's 5x plus 17. Denominator, we can factor. It just looks like the previous problem, though. Look like this problem. X squared minus x minus 6. Yeah, exactly the same. So we can factor the denominator as x minus 3 times x plus 2. Negative 3 and the positive 2 multiply to negative 6, add up to negative 1. And since we have 2 roots for the denominator polynomial, we have 2 vertical asymptotes. The 2 vertical asymptotes are x equals 3 and x equals negative 2. This function, since the denominator polynomial has 2 roots, the graph has 2 vertical asymptotes. One is x equals 3, the other is x equals negative 2. 3 would make the denominator be 0. Negative 2 also make the denominator be 0. So that's how do we find the vertical asymptote. Horizontal asymptote. We want to look at the original format of the rational function, not the factored form. Since the degree of the numerator is 1, degree of the denominator is 2. So when you let x approaches infinity, the denominator runs a lot faster because it has degree 2. And so we basically can see the numerator, like doesn't move and the denominator move. So when you have something, numerator stay the same, denominator run to the infinity, of course the whole function, the whole quotient runs to 0, right? For that reason, the horizontal asymptote is y equals 0. Y equals 0. You can actually summarize if the degree of the bottom is bigger than the degree of the top, then y equals 0 is the horizontal asymptote, always. Yeah, the reason, as I trying to show you, is when x approaches infinity, the denominator runs super fast, faster than the numerator. So we can assume the numerator doesn't move and the denominator runs to infinity. So that would make the quotient runs to 0. I hope it makes some sense.
I have a question real quick.
Yes, please.
I'm not sure. I think I might just be forgetting, but what does it mean to find the whole of the rational equation function? Like, what does that mean? What is the whole?
The whole is when the numerator and the denominator, after you factor them, they have a common binomial factor. Yeah, we will have an example. I might have an example like that. I designed to have that one of the example. For example, since you are asking, this factored form of a rational function has a whole as at x equals 1, has a whole, HOLE. Means you can get rid of them, right? You can cancel. Because x minus 1 is a common factor of the numerator and denominator, so you can cancel them. But you cannot just simply cancel them. You have to denote x cannot be equal to 1, cannot be 1. 1 will still make the original rational function undefined. So basically, the rational function has the same graph with this part, but is not defined at 1. So it has a whole at 1. Did I answer your question?
Yes, thank you.
Okay. Appreciate that question. Yeah, we will have a question like that later. I have those problems. They kind of like represent different situations. Okay, vertical asymptote. It has 2 vertical asymptotes. It has 1 horizontal asymptote. And that's everything. And I have this graph here. You can also get the graph by using graphing calculator. As you can see, this rational function has 3 branches. Yeah, it has 3 branches. That make 2 vertical asymptotes possible and 1 horizontal asymptote at the x-axis. Next. This rational function has a polynomial in a numerator has degree 2. The denominator has degree 1. So this type of rational function is going to have a slant. Is going to have a slant asymptote. All right. We still need to identify the vertical asymptote. And you can note if the degree of the numerator is bigger than the degree of the denominator, then the rational function has a slant asymptote. This one is the case. We'll still consider the vertical asymptote. The vertical asymptote is x equals -8. Because -8 would make denominator be 0. So it means when x approaches -8, the denominator approaches 0, and the numerator approaches to a fixed number, constant. So if the numerator stay as a constant, denominator approaches 0, the quotient approaches infinity. That's how do we know the vertical asymptote is x equals the root of the bottom. So that's the vertical asymptote. What about the slant asymptote? To find the slant asymptote, we wanna use long division. We wanna use long division. We wanna actually divide the numerator for x squared plus 35x plus 31 by the denominator, which is negative x minus 8. We actually, you know what, we can modify the rational function a little bit and use a synthetic. Let's use synthetic. I'm going to do this, okay? I'm going to multiply both top and bottom by -1. Then the denominator gonna become x plus 8. And the numerator is gonna become negative 4x squared minus 35x minus 31. Okay, one more time. What did I have done just now? I multiplied both top and bottom by -1. The benefit of doing this is we have the divisor right now in the format x minus k, and we can use a synthetic method instead of long division. And the k here is -8. K here is -8. All right, so let's use the synthetic method. The numerator is already in the standard form. Their quotients are -4, -35, -31. And the k is -8, put it here. Let's use the synthetic method. Bring down -4. -8 times -4, 32. -35 plus 32, -3. -3 times -8, 24. -31 plus 24 is -7. -7. Okay, then the remainder, this is the remainder, is -7. The quotient is -4x minus 3. This is the quotient. When we divide a polynomial by another polynomial, the numerator polynomial is called a dividend. The denominator polynomial is called a divisor. And we can write the quotient of them as the result of them as quotient plus remainder over divisor. This is the formula. So we can write a rational function as quotient -4x minus 3 plus remainder, which is -7, over divisor x plus 8. All right, quotient plus remainder over divisor. And when x approaches infinity, this part approaches 0. When x approaches infinity, this part approaches to 0. Because the numerator is a fixed number, denominator approaches infinity, so the quotient approaches to 0. So the function f of x approaches to the quotient. The slant asymptote is y equals the quotient, 4x minus 3. Question? When the denominator has a higher degree than when the numerator has a higher degree than the denominator, the rational function has a slant asymptote. How do we find that slant asymptote? We can either use long division or synthetic method to find the quotient. When we use the numerator as the dividend, denominator as the divisor. Any question, guys? If any part is not clear, also please let me know. Maybe I can explain better.
That all seems pretty clear.
Oh, okay, thank you. Thank you for your response. Then let's move on. Number 4. Number 4, numerator degree 2, denominator also degree 2, okay? And we want to see if we can factor the numerator and denominator. We have to factor all the time. That's the reason foundation 2 factoring polynomial is very important because you use that all the time in pre-cal. So we want to see how to factor the numerator and denominator for this rational function. I'm going to use my trick, okay? 1, 2, 3, 3. 2 times 93, 96, 96 plus 3 is 93. So numerator can be factored as x minus 3 times 2x plus 3. You can use whatever the method you feel comfortable to factor it. And the denominator, also quadratic trinomial, 1, 3, 2, 5, negative, negative, negative 6, negative 5, negative 11. So the denominator can be factored as x minus 2 times 3x minus 5. Double check. Negative 6, negative 5, negative 11. And this one, negative 9, negative 6, plus 3. Okay, that's correct. As we can see, the numerator and the denominator do not have a common factor. That means there's no whole. There's no whole. And we would have 2 vertical asymptotes because the denominator has 2 roots. The first root, x equals 2. Second root, x equals 5 over 3. All right, 2 and 5 over 3 are the 2 numbers that would make the denominator be 0. So the rational function has 2 vertical asymptotes. One is at 2, x equals 2. The other is at 5/3. So x equals 5 over 3. And that's a vertical asymptote. Horizontal asymptote. When the degree of the top and the degree of the bottom is the same, then the horizontal asymptote is y equals the quotient of a leading coefficient. Leading coefficient. All right. So the numerator has degree 2, denominator also has degree 2. So the horizontal asymptote is y equals a quotient. Quotient of what? Quotient of the leading coefficient of the numerator and the leading coefficient of the denominator. So the horizontal asymptote is y equals 2/3. Just like that. I have the graph actually. As you can see, the graph of the rational function has 3 branches. There's one here, very small. Can make it bigger. Do you see the top? There's one branch on the top. So 3 branches. It has 2 vertical asymptotes. One is as x equals 2. The other is at x equals 1 point something, smaller than 2. And the horizontal asymptote is y equals 2/3. And that's this problem. Number 5. Numerator, degree 2. Denominator has degree 2. We want to factor. Yeah, the first thing to do is always a factor. X numerator can be factored x plus 3, x plus 7. 3 and 7 multiply to 21, add up 10. Denominator can be factored as x plus 3 times x plus 6. 3 times 6 is 18. 3 plus 6 is 9. Let me double check. 3, 7, 21, 3, 7, 10. 3, 6, 18, 3, 6, 9. Okay, this one has a whole because numerator and denominator has a common factor x plus 3. So we can cancel them, right? But don't rush. You cancel them, you have to denote here. X cannot be negative 3. X cannot be negative 3. All right? We cancel this part, but it doesn't change the fact negative 3 is not in the domain of the original rational function. So we have to denote x is not equal to negative 3. Very, very important. It's just the function does not have a vertical asymptote at negative 3. It's going to have a hole. It's going to have a hole at negative 3. So the graph f of x, the graph of f of x and the graph of g of x, after we get rid of the common factor, have the same shape, but the difference is this function x cannot be negative 3, but g of x does not have that requirement, right? But in order for them to be equal, you have to add this condition, x cannot be negative 3. So let's say the graph of x plus 7 over x plus 6 is like a hyperbola like this. It's just at negative 3, you're going to have a hole here. You're going to have a hole here. All right? So when the numerator and the denominator has a common factor, then that's how do we know the rational function has a hole. Has a hole at x equals negative 3. Has a hole as x equals negative 3. Because negative 3 is not in the domain. And the vertical asymptote is x equals negative 6. Yeah, we still have this roots in the denominator. X equals negative 6. Horizontal asymptote. Horizontal asymptote, you look at this quotient after you get rid of the common factor. Numerator degree 1, denominator degree 1. So horizontal asymptote is the quotient of the leading coefficient. 1 over 1 is 1. Please let me know, do you have any questions?
Could you show us what the hole looks like on a graph?
Yes. I can draw the graph for you. Does that sound okay? So x plus 7 over x plus 6 is 1 plus 1 over x plus 6. So basically the mother function, reciprocal function, move to the left 6 units. So negative 6, comma 1, 1, 2, 3, 4, 5, 6, comma 1. So this is the graph is going to be like this. Where's negative 3? Negative 1, negative 2, negative 3. But it has a hole here. It has a hole here. This is the graph of the original rational function. Is a hyperbola with a hole in the top right branch. Does that make sense?
Yeah, I think I kind of get it now.
Yeah, okay, very good. Okay. Do we have one more? Okay, we have one more here. Numerator degree 2, denominator degree 2. We need a factor. X plus 8, x minus 1. You need to be able to quickly get them done. Positive a, negative 1, multiply to negative a, add up to 7. And the bottom, x plus 4, x plus 8. 4 times 8 is 32, 4 plus 8 is 12. Okay, as you can see, I'm gonna switch the order. X plus a, x plus 4. This way you can see the better. X plus 8, as you can see, is common, right? That means this rational function as a whole. The rational function as a whole at x equals negative 8. All right, as at x equals negative 8. And the vertical asymptote. So after you identify the whole, you can get rid of this part. So for the vertical asymptote and the horizontal asymptote, you only need to look at this part. Okay, if you make it better, you have to write x cannot be negative 8. Just something very strict detail. And the vertical asymptote, x equals negative 4, right? Because negative 4 is the 0 of the bottom. And the horizontal asymptote, since the numerator because the numerator and denominator both have degree 1, the horizontal asymptote would be the quotient of the two leading coefficient. Leading coefficient on the top is 1, bottom is also 1, so y equals 1. I can also show you the graph of this rational function. The graph of the original rational function has the same shape with x minus 1 over x plus 4, but has a hole at x equals negative 8. And let me show you how do I quickly graph x minus 1 over x plus 4. I would write the numerator as x plus 4 minus 5. 4 minus 5 is negative 1, right? So it's equivalent, and x plus 4. And then I'm going to split the quotient as a 2 quotient. So we have x plus 4 over x plus 4 plus negative 5 over x plus 4. Yeah. So we have 1 plus negative 5 times 1 over x plus 4. So this, I think the branch is going to be in when x is negative. When x is negative, yeah, in left top and the right bottom. And then with the center is at negative 4. And the horizontal asymptote is 1. Okay, it's also vertically stretched by factor of 5, but it's hard to draw that transformation. So basic shape is like that, okay? Basic shape. And at negative 8, it will be somewhere around here. It's negative 4, around negative 8. It has a hole here. So the graph is a hyperbola. 2 branches with a hole on the left top branch right here at the negative 8. All right. We can make a we can summarize for finding horizontal, vertical, slant asymptotes and a hole. Then you know at least how to do the related problem quickly. First thing to do is to factor the numerator and denominator. Okay, first thing to do is to factor the numerator and denominator. If the numerator and the denominator has a common factor, that means the rational function has a hole somewhere. And you get rid of the common factor. And then you look at the vertical asymptote and the horizontal asymptote, all right? If the numerator and the denominator have the same degree, then the horizontal asymptote is the quotient of the leading coefficient on the top and the leading coefficient on the bottom. Like this one, 2/3. And this one, 1, right? 1/1, y equals 1. If the numerator has degree less than the degree of the bottom, like this one, the numerator has degree 1, denominator has degree 2. Then the horizontal asymptote is the x-axis, y equals 0. If the numerator has bigger degree than the denominator, like this one, then the rational function does not have a horizontal asymptote, is gonna have a slant asymptote. How do we find the slant asymptote? We use either long division or synthetic method to find a quotient and make y be the quotient. Then that linear function or the straight line, this is a straight line, is the slant asymptote. For vertical asymptote, it's just the 0 that make the denominator be 0. It's not whole, okay? If the value make both top and the bottom be 0, then the rational function has a hole at that value. If the value only make the denominator be 0, then the function has a vertical asymptote at that value. Well, I'm very clear. I'm just, this is new to you. You're gonna let me know which part is not clear and let me know, please. Ether? Is this understandable?
I'm trying to understand it. I can go back to the video. It's okay. I'm trying to.
Yeah, we have this many questions. They have different, situation, cover all the possible situation.
The first few questions we've been doing, I totally understand. Yeah. Like this one is kind of different from.
Which one? Number 4?
Yes, this number 4.
This one? Okay,
yeah.
number 4. Number 4 is not that difficult. So firstly, you factor the numerator and denominator, right? And then you notice no common factor. That means the rational function has no hole.
No hole, okay.
Yeah, the hole only happens when there is a value of x that could make the numerator be 0 and the denominator be 0.
Okay.
Right? Yeah, but there isn't such a value because the numerator and denominator do not have a common factor. So no hole. On your scratch paper, you want to write no hole. And then for vertical asymptote, you just need to find the value or values only make the denominator be 0. 2 make the denominator 0. 5/3 make the denominator be 0. So the function has 2 vertical asymptotes. For the horizontal asymptote, you look at the degree of the numerator and the degree of the denominator. If the degree of the top and the bottom is the same, then the horizontal asymptote is y equals a quotient. The quotient is the quotient of the leading coefficient, is 2/3 in this case. Better?
Yeah.
Okay. All right. Yeah. Next one, I want to show you the 3 types of asymptotes of a rational function using Lumen 3.5, question number 9. I'm going to stop share this notes and share the Lumen again. This one. Question number 9. Question number 9, kind of like application of the stuff we have been learning today. Okay, let's look at those 4 functions. And it also gives 4 graphs. We just need a match. We need a match. First function, numerator linear, denominator linear, right? So degree 1, degree 1. And as you can see, this function is going to have a vertical asymptote as x equals b, and a horizontal asymptote. Anybody can tell me what's the horizontal asymptote, please? What's the horizontal asymptote of this function? Degree of the top is the same as degree of the bottom. So the horizontal asymptote is y equals what? Quotient of, yeah, exactly, thank you. Let's look at the 4 graphs. Which one has a horizontal asymptote as y equals 1? This one doesn't look like that. B, x equals 1. No, this one cross at 1. Y equals 1, sorry, y equals 1. And this one, y equals 1. Okay, this one is, seems like y equals 1 is horizontal asymptote. However, the shape of the graph isn't right. This one more like it. This one, okay? This one has vertical asymptote at here and a horizontal asymptote at y equals 1. Horizontal asymptote matches, and the shape is also works because when the top and the bottom both are linear, it's gonna be look like a hyperbola. Okay, it's gonna be a hyperbola. So this one is D. For the second function, it has a vertical asymptote at x equals b. Since the numerator has degree 2, denominator has degree 1. Please answer me. The second function, does this function has a horizontal asymptote? Does this function has a horizontal asymptote?
No.
No, yeah, you're right. What kind of asymptote it has?
A slant.
Slant. Very good. Awesome. So we need to look at the 4 graphs. Which one has a slant asymptote? B. Do you see that? B has a slant asymptote, right? So B is this one. C, no, the next function. The next function, it has one as vertical asymptote because x equals b. And the numerator is degree 2, denominator is degree 2. Anyone can tell me what's the horizontal asymptote?
Is 1.
Yeah, y equals 1. So earlier we see a graph has asymptote equals 1, right? Like this one. It looks more complicated because numerator and denominator both has degree 2. So I would say this is a C. And the last one, vertical asymptote happens at x equals b. Anybody can tell me what's the horizontal asymptote?
A.
Y equals, yeah, when the numerator has degree 1, denominator has degree 2. What's the horizontal asymptote?
0.
Yeah, y equals 0, the x-axis, right? Which one has the x-axis as the horizontal asymptote? This one, right? This one is not, it is crossed. This one is not also touched. This one is not, so it has to be A. All right, guys. I think we got it right. Yep. That's everything for today. Mainly, I would recommend when you encounter a rational function, use the graphing calculator to help you understand the connection between the function and the graph, asymptote, vertical, horizontal slant, and a hole. All right, guys, that's everything for today. Feel free to email me if you have any questions.
Thank you, Professor.
Okay.
All right. Thank you. Goodbye.
Goodbye.